This part will be the material. This part will be optional. It won't be covered in the exam, but it's nice and it will explain why RSA work. I would start with this because people would show up late, so I don't want them to miss the actual stuff that would be on the exam. All right. So we discussed a little bit about some of the histories and Fermat, who is really famous because of the theorem that he didn't prove, but he claims to be true. So it's this one. So let me remind you again. So there's a margin in his note, and he said like a to the n plus b to the n equals c to the n does not have integer solutions for n larger than 2. You know, when n equals 2, that's Pythagorean theorems. And he claims that, so let me try to be Fermat. Let me say, I have, okay? He didn't wrote this because he's French, so he would wrote it in French. Okay? But this is like, people call it Fermat last theorem. People spend, not people, mathematicians spent like 100 years proving it, and it was proven in the last century. So probably one of the most famous theorem in the last century. Okay. Today we learn about the Fermat, the other theorem called Fermat-Little theorem, and we will be able to prove it pretty, not easily, but it'll be nice. Okay. But the reason I talked about this is because it is connected to two topics that we have discussed. One is the RSA. Okay. So to prove that RSA is correct, we use another theorem called Euler theorem. And Euler is another fascinating mathematician, but it's closely related to the Fermat-Little theorem. Okay, it's like roughly looks the same. Okay, and also it will give you part of the primality testing. Last time we discussed a little bit about like prime numbers and internet security, right? You want to have prime numbers because you want to use RSA, okay? And RSA is like the backbone of internet security these days. So you want to check, you want to pick a random prime numbers which is really large. How can you do that? You just pick some random numbers and check if it's a prime or not. So how could you do that? We use the algorithm that do that. The algorithm that does that use Fermat-Little theorem. So that's why we look at it today. Okay. Okay. So the key thing that you need to remember today and for the final is like, so if you have integer a and b, so this is what we proved last time using the extended GCD algorithms. So if you have integer a and b, there is an integer a and b. Oh no, if you have integer x and y, there is two integers a and b such that a times x plus b times y equals the GCD of x and y. Okay. We proved it last time using the extended GCD algorithm or extended Euclid. Okay. So this is like what we did last time. Like you should remember this when you go to the exam. Okay. And you should somehow remember why this would say a lot of things. Like for example, if some number is a common divisor of x and y, it should divide this whole term, so it should divide the GCD. So this is the extended GCD algorithm that we experimented last time. Okay, you don't have to remember. Okay, but if you need it, so you can put it in your note. But if I will not ask you to work on it on the exam unless I give you the algorithm itself, because yeah, I hate to have exam which are memorized that you need to remember the algorithms. Okay. Okay. And last time we also talked about, so the reason we talked about this is that we want to be able to say that if So we are thinking about the modular arithmetic. Okay, so we recall that we want to do divisions, but we cannot actually do divisions. We need to multiply. We just multiply the number with the inverse. Okay, so when you want to compute, to compute a over b mod m, for example, you do this instead. So you multiply a with b inverse mod m. So this thing is called the inverse multiplicative inverse modulo m, right? But we know that b minus 1 mod m exists when TCD, so when it's if and only if, okay. If and only if TCD of b and m equals 1, and it is related to this, okay. So we don't really like TCD that much, but TCD allow us to find the inverse, and the inverse allow us to do divisions, okay. So division in modular arithmetics allow you to do a bunch of other things, allow you to solve equations, and today we will learn some other application of this multiplicative inverse, okay. So it's not like, yeah, we are mathematicians, we really love TCD, maybe, but you don't have to like TCD, but the application of it is really useful. Okay, so modular arithmetics is a form of like, congruent is a way to do modular arithmetics in such a way that it looks like the typical algebra that you are familiar with. So when you have two numbers, two integers, we want to say a mod m equals b mod m because we will do everything modulo m. So instead of write mod m everywhere, we just take it out and we write it like this. Okay? So it means a mod m equals b mod m. Okay, and it also implies that m would divide a minus b. Okay. And we also say that this is the most important thing in this part, okay? The concept of multiplicative inverse. So the multiplicative inverse of a modulo m is a number that if you multiply with a equals 1 mod m. Okay? We can use the multiplicative inverse to sort of like cancel out a. Okay? And you can do division with it. Okay? And this is what we proved last time. I'm not going to prove it again. A has a multiplicative inverse modulo m if only if the TCD is 1. Okay. So let's get to the primality testing. Okay. Again, checking if a number is prime is a really fundamental algorithm that you need if you want internet security. So we look at it a little bit. Okay. To test if a number is prime, you can just keep dividing the numbers. But if the number is really large, you will not be able to do that because the running time will take the factor of square root n, but n is like, yeah, astronomically large. So it's not going to be feasible, and this is not polynomial time algorithm. So what else can you do? Okay, so you want to check if n is a prime. If there's a property that's true when it is if and only if n is prime, we can, instead of just checking the number itself, we can check that properties. Okay, like you have the definition of odd even numbers, and we say an even number, a number is even if there exists some integers such that blah blah blah, right? To check this property exactly, you need to find that integer, right? But you can just try to divide by 2. So we know that if the number is even, you can divide it by 2 and get a remainder of 0, right? So you can do that. That would be properties. So instead of checking the definition itself, you can check the properties. Okay. So if there's a property that we can check quickly, we can check if it's a prime. But sometimes that's probably is too good to be true. So if we only have the property that holds only when it's prime, can we use that properties to check if n is prime? So let me be clear. So there's some property P, okay? So if P is true, if and only if n is prime, we can just check this property, okay? If this property is true, then we know that n is prime. If this property is false, then we know that n is not prime, okay? Now, if we have a property that looks like this. So if n is prime, this property is true. Can we use this property to check if n is prime? So suppose we check this property and we see that this property is true. Can we conclude that n is prime? No, right? Because this is like Q implies P, and you know P, you know nothing about Q. Okay? However, if you check this property and you find that this property is false, what can you say about n? If this property is false, what can you say about n? N cannot be prime, right? Because we know that if n is a prime, this property has to be true. But if it turns out that this property is false, we know exactly that n is not prime. So sometimes this property is sort of like give you the evidence that the number that you're looking at is not a prime number. It cannot be used to show that it's a prime number, but in some case it can be used to show that, oh, alright, this is not what I want. Okay? And what are these properties? So it's this one. It's this Fermat theorem that we proved today. Okay? So the Fermat theorem says this. It might not look, it probably doesn't make any sense why you want this kind of theorem, but it's really nice and it's very useful. Okay, so it says that if P is a prime and A is an integer such that GCD of A and P equals 1, so A is not, A doesn't have, so since P is a prime, right, if GCD and A and P equals 1, it means like P is not a factor of A. Okay, because P is prime, the GCD of anything with P is going to be either 1 or P itself. Right? So, because if it's not 1, then there should be some common factor between A and P. But P is a prime number, it has no other factors, right? So, if you divide P, it should be 1 or P. So, if the GCD of A and P is not 1, it has to be P. And it means that A is multiple of P. Okay? So, if GCD of A and P is 1, then we know that if you raise A to the P minus 1 power, it's going to be 1 mod P. Okay? So, it might not make any sense why you want this kind of theorem, but it will be useful later. Okay? So, how can we use this kind of theorem to check if P is a prime number? Yeah. So, this theorem says if P is prime, okay, and GCD of A and P equals 1, okay, then this has to be true. So you want to use this to check if number n is a prime or not. You can just, if n is a prime, then you can pick some number A, okay, which has GCD of A and n equals 1. And then you check this, if this is true or not. So this is the algorithm. This is the algorithm that checks prime number. Okay? So you want to check if n is a prime number. The previous theorem is true for any integer n, for any integer a. Sorry. Right? For any integer a, if you raise to the power p minus 1, right? So I don't know which a to pick. So I pick one number randomly from this range, and then I do two check. One, I check if GCD of A and n is 1 or not. So if the GCD can be computed really quickly, right? If you remember, GCD can be computed like in O log something, right? It's very efficient. So you can compute the GCD of A and N. Okay. So if the GCD of A and N is not 1, what do you have? What do you know? A is from 2 to n minus 1, right? Less than n. And the GCD of A and n is not 1. It means that n cannot be prime number. Because there are common factor between A and n, right? So if n is a prime number, definitely the common factor between all number from 2 to n minus 1 should be 1, right? So in this case, you say, oh, okay, n is not a prime number. But this would be rarely happen because it's really, if you just pick some random number, it's really hard that you pick the factor itself. Okay, like in RSA, if you recall RSA, we pick two large prime number, right? And we multiply it, and it's really hard to pick to pick the number itself. So it's really hard to be in this case. But if it's in this case, it's easy. We know that right away that n is not prime number. Otherwise, when we reach this point, okay, so if n is prime, we also have GCD of A and n equals 1. Okay, so this is basically the assumption of the Fermat last theorem. So this would imply that A to the minus n minus 1 is going to be equal to 1 mod A. So we raise A to the power of n minus 1 modulo n, and we check if Fermat last theorem is true or not. If it's true, if it's not true, when we know for sure that, okay, so n is not prime for sure. Okay, in this case as well, we know that n is not prime. Okay, because if n is prime, GCD will be 1, and if n is prime, the Fermat last theorem would hold. And then if it doesn't hold, then we know exactly that n is not prime. Otherwise, we have no idea. Because it can be the case that n is not a prime number, but somehow this fact is true. Okay, let's go back a little bit. Like the Fermat last theorem only say that if n is a prime, this statement is true, right? It doesn't say that if n is not a prime, what would happen with this statement, right? It might be a case that n is a composite number, and this equation is also true. So if we end up in this case, okay, this case will be like crazy case, so we have no idea. Okay, but we can, but we are optimistic people. We say, okay, I don't know this is not a prime, but so I'll accept it. So I'll say it's a prime for now. Okay, so this is like the case that the other thing might be correct. Okay. All right. So to analyze this Fermat test. Okay, if n is a prime, the algorithm always return true because it will pass all the check and it will return true. If n is composite, Fermat theorem doesn't guarantee that the algorithm will return false. It might return false, then you good. But it might return true, then you got full. So if n is composite, theorem may return false when either GCD is not 1 or this doesn't hold, right? So it violates the property of the Fermat last theorem. But we want to be in this case so that we can say that the number is bad. Okay, but actually we cannot do that. Okay, so the harder part of the primality checking algorithm will be pretty much dealing with this case. Okay, dealing with this case. when the number is not a prime number, but it passed the Fermat test. Okay, how would you do that? I will record a new video and discuss on how to do this later. It will take like half an hour to talk about that. But you should roughly get the idea that the Fermat last theorem is part of the game when you want to check if a number is a prime number or not. Okay? You need some other thing to deal with this because there's some crazy number called Carmichael number. I'm not gonna go through that much. Okay? But let's prove the Fermat last theorem really quickly. So to prove the Fermat little theorem, not the last theorem, okay, we cannot prove Fermat last theorem. If I can prove that really quickly, then I'll be famous. I'll be like, you won't see me here. I'll be like, yeah. But I would love to be able to crack prime number, like to factor large prime number instead, because then I'll be the most famous Bitcoiner. So I can hack RSA. Okay, but all right. So the idea is this: in the proof, we will do something like this. Let's look at the simple case when p equals 7 and a equals 5. Okay, we want to show that a to the 7 minus 1, which is equal a to the 6. It's going to be 1 mod 7. Okay, this is what we want to do. Okay. Let's look at this set. So this set is a number from 1 to p minus 1. Okay, and look at another set. Okay, this is a set that you multiply every guy with a. Okay, a is 5. So I multiply 1 with 5, 2 with 5, 3 with 5, until 6 with 5. Okay, and what exactly is this set? Is this one. Okay, so 1 times 5 is 5, right? 2 times 5 is 10, mod 7 is 3. So is this set. If you look at it, it's the same set. Okay? So you have a set from 1 to n minus 1, or p minus 1, and you multiply with a, you have the same set. Okay? Is it true for every set? In general case, when for general P and A, it will be true. We prove that. Okay, but what do you mean when you have two sets that are equal? It's equal to B, right? It's not a coincidental. We can prove that. But so if they are equal, then if I multiply all the number in the set, it should be equal because it's the same set. So I multiply all the number in the set B, and also multiply all the number in the set C, right? So this is like, I multiply all the number in the set B. Set B is like from 1 to 6, is this number, okay? And then I multiply all the number in set C. And C has this 5, 3, 1. So it's basically the same set, so it's the same number, okay? Because only you have a permutation of number because it is the same set, okay? But what exactly is 5? What exactly is 3? So it's 1 times A, 2 times A, okay? So it's equal to this. I factor it out. There will be A to the 6, and I have this coefficient, and it equals to this, right? And all this number. Later on, we show that all this number has an inverse. So we can basically, we know that this number, this term equals to this. So it look like a to the 6 times 1 times 2 times 3 up to 6 equals to 1 times 2 times 3 up to 6 mod 7. And they all have inverse. So I can cancel out. Okay, I can cancel them out. And I get a to the 6 equals 1. So that's the Fermat last theorem. So that's the proof. So let me go over the proof really quickly. Again, this is not covered in the final exam. It's not part of the final exam. So you can, if you don't really fully understand it, it's okay. It's okay. So the proof is this. So we start with, we assume that the GCD is 1. So for every number, there's a multiplicative inverse. Okay. And look at this set B, and look at this set C. Okay. If I and j are different, then you have AI mod p and AJ mod p to be different, right? And we know that C is of size p minus 1, and all the numbers are in this range, so we can conclude that they're the same. Okay. So basically, every number, so C has the same size as B, and every number in C are different, and they are on the same range. So C has the number from 1 to p minus 1, and they're all different. So they have to be they have to be 1 to p minus 1. So that's the proof that it's the same. So when you know that they're the same, we can rewrite this set. So multiply everything on this set B, and also multiply this thing on set C. They are equal, right? So we write the whole thing like this, and we get this term. And then since all this number has inverse, like all this number has inverse, so I can multiply by the inverse, right? If I multiply by inverse of 1, I can cancel 1. If I multiply by inverse of 2, I can cancel 2. And I keep cancelling all out. Then I get 1 equals p to the a to the p minus 1 mod p. So this is the Fermat last theorem. Oh, sorry, I really confused. Okay, this is the Fermat little theorem. Okay, that we can use to test the prime number. Okay. All right. So how good is Fermat test? So when n is a composite, Fermat test might not guarantee that you have this. Okay. But we really want the number a to be such that it would reveal the fact that n is composite. Okay. So when it's composite, we want the check prime algorithm to say it's composite. So we want a to be such that it violates the Fermat last theorem, Fermat little theorem. Sorry. Oh, okay. I need some more sleep. Okay. But there are typically, if n is not a bad number, okay, I'm not gonna say a bad number, bad composite number. There will be a lot of a that would reveal the fact that the number n is not prime. But there are some really bad numbers called. So we say a is a witness if a reveal the fact that n is not prime. So I'm not going to talk about it that much, okay? I'm going to go really fast. But there's some number called Carmichael number that sort of like break it, and the other thing doesn't work for this number. So to build the actual primality testing algorithms, you need to deal with this, and there are some number theorem that you can use in some other ways. You can check the number, okay? So I'm not gonna go over that, but that should be if you are interested in this, I can have a video that you can watch. Okay. All right. So okay. So that's it. That's it for the Fermat little theorem. You can use it to check if a number is a prime. But I'll show you a related theorem that we have used. We actually use it when we perform the experiment on RSA. Okay, so it's called the Euler theorem. You should take a minute to take a look at this form. Okay, so a is a prime number. No, p is a prime number. So you raise a to the power p minus 1, and it's going to be 1. Okay. Now, you might wonder if you have another prime number, what would happen? Okay. So it's the Euler theorem. It's the special case of the Euler theorem. Okay. If you have two prime numbers, if you have two different prime numbers, okay, and if you have A such that GCD of A and PQ equals 1, okay. If you recall when we worked on RSA, we need to make sure that the message that we encode, the GCD of the message that we encode with the n, parameter n. Think about RSA, okay? If you recall RSA, we pick two large prime number, right? And we multiply them and we get n, okay? And we perform everything modulo n. And n is known, okay? N is part of the public key, okay? So if you have a message such that GCD of A and PQ is 1, then we have this. We know that P to the power of A, the A to the power of P minus 1 times Q minus 1 equals 1 mod PQ. Okay? So this is the Euler theorem. You can prove it in the same way as we did with the Fermat-Little theorem. Okay? To prove that, we need to count the number of number with GCD equals 1, and that was part of the homework as well. Okay. Anyway, you can prove this using the same idea as the Fermat-Little theorem. Okay. Now let me show you that this would imply that the RSA algorithm that we did last time is correct. So quick review: the RSA algorithms, you pick large prime, right? Pick primes P and Q and let n be PQ, right? And then you should select E and D, right? In such a way that after you encrypt and decrypt, you get the same thing, right? Mod n. Okay. So the way you do that, you pick two prime numbers P and Q and let n be PQ, and you pick E. So we pick E to be, last time we picked E to be 6, 5, 5, 3, 5, something like that, right? And then we compute D, right? D will be part of the private key. E is part of the public key. Okay, so we pick D such that D is a multiplicative inverse of E modulo this. Okay, this is crucial. So when did we do this? If you go back to the Colab sheet, there's one step that we compute D. Okay, when we compute D, we find the inverse of E modulo P minus 1 Q minus 1. Okay, if you go back and look at that code in Colab, you see that it's basically the extended GCD algorithms that we learned. Okay, so we pick D in such a way that this is true. So ED equals 1. So D is the E inverse, right? So ED equals 1 mod this. Okay. Now, what exactly is this number? Okay. Again, when we do encryptions, I'm gonna go over this really quickly. Okay. So when we do encryption, we raise the message to the power of E, and when we do the decryption, we take the encrypted message and we raise it to the power of D. So this is the result of the encryption, and then you decrypt. You want this number to be M, so you want the message back. Okay? You want this to be the message. Okay? But what exactly is this? So let's try to analyze it. What is this number? So M to the ED. What is it? So we know that ED is 1. Okay, ED equals 1 modulo this, right? So if you take ED, you can write ED as, so after you divide ED with P minus 1, Q minus 1, you get the remainder of 1. So ED is of the form like this. Okay, so you divide ED with P minus 1, Q minus 1, you get the remainder of 1. So you can write ED like this, and k is in integers. K is in int. Okay? So we write it this. So m to the ED is going to be m to the k times p minus 1, q minus 1, plus 1. And we do everything modulo n. Okay? Now, this is 1, right? So you can factor m out. So k to the p minus 1, q minus 1 times n, mod n. Okay? Alright. So, but what exactly is this? M to the k times this. So, I would factor k out once more. But I really hate to write it, the whole thing. So, I write it like this. M to the p minus 1, q minus 1, and I raise it to the power of k, mod n. But what exactly is this? This part, the Euler theorem says that this part is 1. Okay? If you go back, you can see that this is 1. So a to the p minus 1, q minus 1 is 1. So this term is 1 from Euler theorem. So 1 to the power of k is 1, right? So this is going to be equal to m mod n. So you encrypt m and decrypt m and you get m. The fact that you get m back is because the Euler theorem is true. Okay? The reason why you get this is because you pick E in a clever way. You pick E in such a way that E times D equals 1 mod this part. Okay? So it's sort of like, yeah, this is pretty beautiful math. Okay? And you can decrypt the whole thing. Okay? So this is why RSA works. Okay, so it's down here. So you really need to make sure that m is not we say this like relatively prime to n. So the factor between m and n is 1. Has no common factors. If you have a message that has common factor with n, your encryption won't work. And also this message would reveal the factor of n, right? So it would break your encryption anyway, right? Okay. So so you might not fully understand all this, but you should sort of like see why the number theories and Fermat little theorem and Euler theorem is useful, because it's something that you use like every day. When you use HTTPS, okay, the first step is to do the key exchange with the server. You do that using the RSA protocol, and it computes something like this. And it works because the Euler theorem. Okay. Right. Okay. So first part of today. That's it.